Dear students, welcome to the online class. I am Dr. S.S.C. Hiremat. In this video, you are going to study about the heterogeneous catalysis. If the reactants and the catalyst are in the different phases, it is called heterogeneous catalysis. It is also called the contact catalysis or the surface catalysis. Here, we are going to classify the reactions into unimolecular and bimolecular. Here, in this video, you are going to study about the kinetics and mechanism of unimolecular reactions. About mechanism. Suppose A is one reactant. It absorbs at the surface. That is S is the surface. Then the intermediate complex AS is formed. Suppose it takes place with rate constant K1. Thus, we may number this equation as 1. Then the intermediate complex AS dissociates to give the reactant and the surface area is freed, and this takes place with rate constant minus K1. That is K minus 1. That is equation 2. This equation 2 is just the reverse of equation 1. The intermediate complex AS, it decomposes to give the product, and the surface is liberated, and it takes place with rate constant K2. We number this equation as 3. Okay, we can apply the steady state principle to the intermediate complex AS. Applying steady state approximation to AS, we get dAs divided by dt is equal to the change in concentration of AS is by the formation of this from this equation. There is K1 into concentration of A into concentration of S, and decomposition takes place by this equation, that is minus K minus 1 into concentration of this AS, and this also decomposed to give the product by this equation, minus K2 into concentration of AS. Okay, now we can make this equal to 0, means we are applying here the steady state principle. Okay, on rearranging this, here in the both the cases AS is there, we can take AS as common, that is intermediate complex forward is taken as common, then this becomes K1 into A into concentration of S, this remains as it is. Then if you take that side, these two terms will be in the denominator, that is K minus 1 plus K2. We are getting the equation this. Suppose this is equation 4. By applying the steady state principle, we get the expression for concentration of AS. Suppose total surface area is 1. That is fraction of total surface area. Absorbed is theta. Then vacant area, that is vacant surface area. Okay, vacant surface area is equal to 1 minus theta. That is vacant surface area is 1 minus theta. Then here the AS is formed at the surface. Then the concentration of AS, it depends upon the concentration of the total fraction of the total area absorbed. Okay, then one proportionality constant is CS. Thus the concentration of AS is directly proportional to theta, and proportionality constant is CS. Thus we get this. Then there is vacant area, the sites which are available for the absorption. Here this indicates the vacant area. The vacant area is directly proportional to 1 minus theta. That is free area. Okay, that is free surface area, and this is also given by the constant, this proportionality constant CS. Okay, thus you are going to get this. Then you substitute the values. Okay, substituting in equation 4. Substituting in equation 4, we get what is that? AS equal to CS into theta. That is CS into theta. Then K1 AS, K1 into concentration of A and concentration of S. Concentration of S may be substituted by this. That is CS into 1 minus theta. CS into 1 minus theta divided by K minus 1 divided by K minus 1 plus K2. K minus 1 divided by K2. Then by cancellation these two CS, we get theta is equal to K1A divided by K1A theta divided by 1 minus theta. Let us take this also. 1 minus theta, that is equal to K minus 1 plus K2. Okay, then you invert this. On inversion, what happens? 1 divided by theta minus theta divided by theta means 1. That is equal to K minus 1 plus K2 divided by K1 into concentration of A. Then 1 minus theta equal to, then 1 divided by theta equal to, you take 1 this side. That becomes K minus 1 plus K2 divided by K1 into concentration of A. This is plus 1. Then we get that is 1 divided by theta equal to, that is 1 divided by theta equal to K minus 1 plus K2. Then LCM is K1 into A divided by K1 divided by K1A, that is K1A. Okay, then on inverting this, you are going to get theta equal to K1 concentration of A divided by K minus 1 plus K2 plus K1 into theta. Suppose this is equation 4, 5, and we may substitute this is equation as equation 5. Okay, from assumptions, that is rate is directly proportional to theta and proportionality constant is K2, where K2 is a rate constant. This is from our assumptions or postulates. Okay, thus we get rate equal to that K2 into theta, that is K1 into concentration of A divided by K minus 1 K2 plus K1 into A. This is K1 not A, this is K1 into A. We get this equation. This is the expression for the rate of the unimolecular adsorption. Here concentration of A is equal to pressure. Then what we get? Rate equal to K2 K1. Concentration of A is replaced by PA divided by K minus 1 K plus 1 K2 plus K1 into PA. This is equation 7. Equation 7 is the expression for the rate of, this is unimolecular heterogeneous catalysis. Now about the conditions, cases. case 1. Okay, when Pa is very very small, that is applying condition when K minus 1 plus K2 is very very smaller than K1 into Pa. K1 into Pa, which is larger? This is larger. This is negligibly small. Then equation becomes K2 K1. Okay, when this is large, this is neglected, K1 Pa get cancelled, that is K1 Pa is then rate equal to, okay, then rate equal to, what is that, K1 K2 Pa divided by K1 Pa. This is nothing but the K2, that is zero order reaction. Means when the pressure is very high. Then another condition when K1 minus and K2 is larger than K1 Pa. Okay, K1 Pa. Then which is smaller? This is smaller. This is considerable. And if it is neglected, you are going to get rate equal to K2 K1 or K1 K2 Pa divided by K minus 1 plus K2. Means it depends upon, suppose these are all the constant, it is directly proportional to Pa. Then it is first order reaction. This is first order. The reaction becomes first order when Kpa is low. The same can be represented with the help of a diagram. In this case, which are variable in the equation 7, rate is variable with Pa. Thus we can plot a graph of pressure of A or Pa, and here this is rate. Okay, we are going to get a curve of this nature. Okay, what it shows, when the pressure is very low in this area, when pressure is very low, means this is smaller than this. Okay, this is smaller than this. When Kpa is smaller than this is first order. Therefore, the reaction is first order. Okay, when pressure is very low. And when the pressure is high, means at high pressure here, the reaction is zero order. Thus we can apply the conditions when pressure is very low, this is first order, and the pressure is very high, this is zero order. This equation defines all the conditions. That means a reaction may be zero order or it may be a first order. It depends upon pressure of the reactants.